In the world of computer science, data structures are the bedrock upon which complex software is built. Among these fundamental structures, the stack stands out as remarkably simple, yet incredibly powerful. Imagine a stack of plates. You can only add a plate to the top and remove one from the top. This principle, known as last in first out, or LIFO, defines how stacks operate and underpins their importance in modern computing. Stacks are everywhere in our digital lives, often working behind the scenes to ensure the seamless operation of our devices and applications. From the websites we browse to the code that powers our smartphones, stacks play a crucial role in managing and processing information efficiently. Their impact is profound, influencing everything from how our programs execute instructions to how data is stored and retrieved. Understanding the fundamental principles of stacks is essential for anyone looking to delve into the fascinating world of computer science and software development. As we explore the intricacies of this data structure, you'll gain a deeper appreciation for the elegant solutions it provides to a wide range of computational challenges. The beauty of the stack lies in its simplicity. It operates on two primary principles: push and pop. Push refers to adding an element to the top of the stack. Imagine placing a new plate on top of your stack of plates. Pop refers to removing the top element, much like taking the top plate off the stack. This straightforward mechanism is what makes stacks so efficient for certain tasks. Let's consider a real-time example: your web browser's history. Each time you visit a new web page, the browser pushes that page onto the history stack. When you hit the back button, the browser pops the last visited page off the stack, taking you back to the previous site. This simple mechanism, powered by a stack, allows for seamless navigation through your browsing history. Beyond push and pop, another important operation is top. Top allows you to peek at the element currently at the top of the stack without removing it. Think of it as checking the color of the top plate without taking it off the stack. These three operations, push, pop, and top, form the fundamental building blocks of stack data structure. The applications of stacks extend far beyond web browsing history. They are deeply embedded within operating systems, compilers, and various software applications. In system software, stacks play a critical role in managing function calls. When a program calls a function, the system pushes the function's return address onto the stack. Upon function completion, the return address is popped, ensuring the program resumes execution from the correct location. In the realm of compilers, stacks are instrumental in parsing and evaluating mathematical expressions. By converting expressions into postfix notation using stacks, compilers can efficiently evaluate them. Consider the expression 2 + 3 × 4. A compiler using a stack-based approach can break down and evaluate this expression accurately, demonstrating the power of stacks in language processing. These examples highlight just a fraction of the diverse applications of stacks. From managing undo-redo functionality in text editors to implementing backtracking algorithms in problem-solving, stacks provide elegant solutions across a wide range of computing problems. Section 4. Efficiency at its core: stacks in algorithm design. The true power of stacks shines through in algorithm design. Their LIFO nature makes them incredibly efficient for tasks that involve backtracking, recursion, and depth-first search algorithms. In backtracking algorithms, stacks keep track of the steps taken, allowing programs to revert to previous states when exploring different possibilities. Recursion, a powerful programming technique where a function calls itself, relies heavily on stacks. Each recursive call is pushed onto the stack, and as each call resolves, it's popped off, ensuring the program systematically works through the problem. This elegant interplay between recursion and stacks forms the backbone of many efficient algorithms. Moreover, stacks are instrumental in depth-first search algorithms, commonly used in graph traversal and puzzle solving. By using a stack to keep track of nodes to be explored, these algorithms can efficiently navigate complex data structures, highlighting the stack's versatility in tackling diverse computational challenges. Section 5. Conclusion. the enduring significance of stacks. In conclusion, the stack, despite its simplicity, stands as a cornerstone of computer science. Its impact resonates throughout the digital world, from the browsers we use daily to the sophisticated algorithms that power our applications. Understanding stacks is not just about memorizing push and pop. It's about grasping a fundamental concept that permeates the fabric of modern computing. As you delve deeper into the world of software development and algorithm design, you'll encounter stacks time and again. Their efficiency in handling specific tasks, coupled with their elegance in simplifying complex operations, ensures their continued relevance in the ever-evolving landscape of technology. By mastering this fundamental data structure, you equip yourself with a powerful toolset for tackling a wide array of computational challenges.